Hello and welcome to video number 6 on our investigating Cavendish experiment and pendulum oscillations. Now we still are trying to figure out this conundrum that we've fallen into where Cavendish appeared to be, his instrument appears to have an oscillation in his measuring device going backwards and forward, and in the middle of that he's trying to pick up the detection of some sort of gravitational effect or of a mass. However, his needle is continually swaying like this. Now, as we know, any electrical measurement we take our needle and we preload it so it's stationary, and then we measure the deflection according to some predetermined load, and we get a measurement. Same as weight measurement, you know, we don't have our needle moving like this. And I was making fun of Cavendish and his experiment, thinking it's a bit of a, it's not very scientific, it's not very engineered well. However, he may have discovered something. We may have to give him credit for something that, and I may have to apologise. He may have detected what I have detected, and that is extremely sensitive period in the pendulum just before we preload it. Before it's loaded with anything, it just sits there and it's so sensitive to anything. Now, perhaps Cavendish wasn't studying that in his experiment. Perhaps it goes a bit back further, and it was Michel who actually was looking for it. And Michel was using this extremely sensitive zone just before you preload the measuring device to detect the spin of the Earth. And I think it's Michel's experiment that's what we should be looking at. The Cavendish experiment was something I don't know, it just doesn't make sense to me. So we'll be looking at today just our unloaded oscillations again, and quickly we're following on from number 5, which was we had our device spinning in the clockwise direction, which is the same direction as the Earth spins here in the southern hemisphere. And today we're going to do the counterclockwise. Now, what we observed was basically pretty simple. On a stationary Earth, we would expect the oscillation, say, for example, if Michel or Cavendish had discovered this oscillation, this very sensitive zone, we would expect it to be, on a stationary Earth, we would expect it to be symmetrical across a certain axis on the stationary Earth. However, and our oscillation would be equal either side. A would equal B. On a clockwise, we would expect that A would be smaller than B. There'd be sort of more 1 step forward, 2 steps back. And we did notice that. We did see that in our last experiment. Today's experiment will be the counterclockwise direction, where everything was just going the other way. And we just want to see what phenomenon and what that will be. Do we actually get A will be greater than B? Or let's have a look. Right, let's get into that now. So here we have the mechanism upside down, giving us the counterclockwise direction, as opposed to in video 5 where we've seen it in the up the correct way, giving us the clockwise direction. So here we are with the motor disconnected, and our pendulum is 8.5 meters away, and our oscillation without any load is roughly 29 something back to 27-ish. and the time is 20. Yeah, it's at night time, sorry. So that's 2015, 16. And our humidity 77 and our temperature is 16. So our movement is very small, oscillations. I'll go now and turn the motor on, which will make it go in the anti-clockwise direction, and let's observe what happens. Turning the motor on now. Right, we seem to be stabilising at around about that 27 mark. But there is a slight creeping to the left, which would indicate a counterclockwise movement. Alright, it's 2020. I think we'll come back in 15 minutes and just observe what's happened. Alright, so we'll see you in 15 minutes. Let's see what happens in 15, and things will have settled down by then. The optical cable will be under tension from the clockwork motor. But already we can see the left movement to the left is more dominant than the right. Okay, see you in 15. Alright, it's only been 5 minutes, but I'm losing my time distance here. That dot is going to encroach towards the clock. So I don't think there's any point waiting the 15 minutes. Okay, so let's have a look what's happening. Our dot is on the 16, 15, 14, 14, and going back now. Going back
1 unit. Okay, now going back to the left again. There is an oscillation, left and right, but clearly the oscillation is biased now to the left, which is the anti-clockwise direction. Alright, I think we've seen enough. Virtually the same identical happening in the opposite direction as we've seen with the clockwise direction. Sort of 2 steps to 1 step. It seems to be the ratio, something like that. But clearly it is moving counterclockwise. Alright, I think I've got enough information now to go ahead and start building a more accurate Cavendish experiment. I think I know what I need to know now. Alright, from the results of all my experiments over the last, say, 6 months, I'm ready to make a call now on how to set up a repeatable experiment to demonstrate this phenomenon. I guess we could call it the Plumb pendulum number 4 phenomenon, where there appears to be some zone of zero friction when we suspend a plumb bob from a anchoring point. Now, the experiment would go similar to this. We suspend a plumb bob, either with internal lasers or mirrors attached to the plumb bob, being a simpler case, and reflected from an external laser, which would be the cheaper and simplest option to go through. The plumb bob is suspended by an optical cable, which has this property of a zone of zero friction in the neutral position. It projects a light beam onto a distant wall. And what we found was, over a period of time, that several hours to even sometimes a day, the light settles under torsion to a central point. Now, the bob finds this equilibrium through the natural torsion of the cable. It could be any direction, but we usually set it up in a direction that we can measure from at least 8 to 9 metres away to give us a good deviation, because it's almost impossible to see anything closer than say 2 meters from the light, you won't see any deviation. Now what we found was that the bob settles and it bounces or oscillates between 2 points, which is where it hits the torsion of the cable. So it goes, swings around, hits the torsion of the cable and comes back and just oscillates there forever. Now if the Earth was to spin clockwise or anti-clockwise, we would expect that the bob would actually, although its initial inertia would settle in one spot, that the Earth as it spins would take up the torsion beyond that zero friction point in the cable and start synchronizing the bob to the Earth moving from its anchor point in the ceiling. However, we don't see that. What we see is continually the bob sets and rests and oscillates in its zero friction zone. Now, I don't know if anyone's discovered this, but I guess we can call this phenomenon or this effect as a result of the Plumb pendulum number 4 effect. And I'm having trouble explaining it, but at this stage I'm prepared to make an early call from this results that the Earth is actually stationary. Perhaps this was I guess maybe Michel was onto this. I can't see why Cavendish wouldn't have picked up on it as well, but his experiment deviated from that. And then after all, in fairness to Cavendish, he wasn't looking for the spin of the Earth, which he carefully claimed. But still, the spin of the Earth was more important at that stage, because it's still not even 1851 yet when Foucault came to confirm 100% that the Earth was spinning. So there was still argument that the Earth was not spinning back in the days of Michel and Cavendish. So no definite proof. All right, so let's. I haven't, like I said before, I have enough data to go ahead with the next Cavendish experiment, and we'll take it up there again for another experiment. So just before I close here, I just would like to go back onto Cavendish's experiment, just explain again this phenomenon of the zero friction zone within a suspended plumb bob, which his experiment was leading to, and he never picked up on it. So I'd just like to show that a bit more in demonstration. Alright, so this is possibly a demonstration of the most frustrating part of the Cavendish experiment I come across. Now, to me, Cavendish made a very elaborate mechanism that wasn't easily reproduced. Now, I believe the best experiments are those that are easy to reproduce and confirm, rather than this massive, complicated structure that would have been quite complex in the days of Cavendish for anyone to reproduce. Now, what I found was he's working on a torsion balance. His cable is a torsion cable, which is basically a spring balance, just like we have here. We have a little kitchen scales, which is basically a spring balance. And if we look at the back of it, there's just a spring, a torsion spring. Now, Cavendish is trying to measure his gravitational effects, or whatever effects mass has on other mass, in this zone where we've got a massive deviation in his oscillation in his apparatus. Now, if someone said to me, here's a scale, go and measure these coins, these Australian dollar and $2 coins, and there you go, what's that result? Well, you'd say, well, hang on, surely you have to calibrate this thing to stop this, get it into a zone where you can actually get some true measurement. So what we do is we place the spring under a certain torsion and we calibrate it to a point, and then we do our measurement. We don't do our measurement in some oscillating period that's way outside the margin of the thing we're measuring. Yet Cavendish is doing that. So, to me, I do not like it. And to have something, a measurement, these coins, these 3 coins, measuring with an oscillation going across bigger than the actual coin's weigh, to me that's a fraud, or it's a deviation from the true objective. It's more of a magic trick. Alright, so leave that with me, and now I'm about to construct a more accurate I guess Cavendish experiment. So stay tuned and thanks for watching.